Test 1, 2. There we go. Can you hear me?
Yeah, can you hear me?
Yeah, I can hear just fine. Okay.
Awesome.
Let me see. I gotta get voice meter input VAIO. Okay, so I just gotta get your audio into YouTube, and I do. No, audio input. Oh no, it would be audio output actually. Although, yeah. Okay, can you say something real quick?
Yep, I'm saying stuff.
Okay, you are very loud in my mixer.
Uh-oh.
No, it's okay. I'm just gonna turn the mixer down. It should be okay. All right. Oh, actually, I didn't need to do that because you're already piped into cable B. Oh, nice. Okay, so I will just delete that new audio input. Remove. Yes. Okay. All right. I think we're good. And I will start sharing my display. And, oh, and it's very, very big.
Very loud, very big.
Yeah, I mean, why do anything less?
Gotta go all the way.
Yeah. All right, and then my camera needs to go on top of that. There we go. Okay, I think we're good.
All right.
Yeah, and it looks pretty good. Oh, YouTube is saying my video resolution sucks. And why would that be? Output, bitrate, stream. What is my resolution video?
Yeah, I'm getting
Oh.
360p over here.
Yeah, I mean it's set to 280, and output scaled resolution is scaled down. Okay, so I'll turn. Let me stop recording. So, gosh. Okay, that should be good. Boy, there's a lot of belly showing. It's gonna scooch me down a little bit. There we go. All right. Cool. Well, then I think we're good. The current resolution is 2084 by 1152. Well, if it's not optimal, what do you want? I don't know what they want. I don't know, and I don't care. And then
Yeah, it's always I've always have a hard time getting streaming stuff going.
Yeah.
It's very finicky.
And then I'm gonna ignore YouTube chat, and I am just gonna add some text on. And ooh, that ain't right. And I need to turn off my display capture because my clipboard history has got my streaming key in it.
Oh, don't want that.
No. And I'm going to delete it right here because I would very much like to not have that show up. Okay, good. All right, so I'll put that on. Oop. Who knows where it went? Come on, where it just disappeared. Okay, it is off screen, so I'm gonna have to insert that again. Sorry, I tried to get all this done ahead of time.
Oh, no worries.
And we had a very productive morning of demo.
Oh yeah, how's it going?
Well, pretty good. We were intending to. Did I tell you that we changed the scope of our work?
Yeah. You mentioned you're tearing everything down to studs, pretty much.
Yep. And so, I mean, it went pretty well. We think we might actually do a little bit extra, as if we weren't extra enough already, and actually tear the lath out, because the house was built in 1908, so it was originally lath and plaster, and we only have a small portion of original plaster left in the house. But we're thinking about tearing out the lath so that we can replace the insulation, which is only ancillary to resealing the window because it's leaking inside the wall, it turns out.
Oh, okay.
We had one window that had mold underneath it, and it turns out that was fine. It was sampled and it didn't go past the drywall. It was just condensation. And then one of the other windows had water inside the wall. So, and we would have found that out if we hadn't torn down the drywall. So,
yeah, that was I guess a lucky decision.
Yeah, I mean it's an old house. I don't feel like you can make bad decisions.
Yeah, that's fair.
Like when you're deciding between tearing something out or not tearing something out.
Mm-hmm.
Okay. Okie dokie. All right. I'll close all my tabs. And I was going to download one of the Linux images that you have, but I did not.
Okay. I got it working on Windows last night.
Okay.
It's not the most straightforward process, but it's not that hard. It's mostly just like waiting for stuff to install.
Okay.
So I can send a link.
Would it be better for me to screen share my screen in Discord, or would you rather be looking at YouTube?
I'm looking at YouTube. I can see what you're doing.
Okay.
So I'm gonna send a link in Discord. We're gonna set up MSys2, which is like it sets up sort of like a pseudo Linuxy environment in Windows. So if you get the installer from there.
So is this just a command line that's kind of Linuxy?
Yeah, pretty much.
Cool.
If you've ever used Arch Linux, it uses the same package manager.
Okay. I have not, but at least I know what a package manager is.
Also, this is between MSys2 and the virtual AGC repository. This is going to take up like a gigabyte of disk space, just as a disclaimer.
Thank you.
Yep.
But yeah, if my phone wasn't acting as a webcam right now, I could paste demo photos into Discord.
Are you using your phone as a webcam?
Yeah, I need to actually buy a webcam. Not that I use it that often, but I've got an iPhone 12 which has got a true depth camera on the front, and so I downloaded an app that turns It streams camera footage, and if you have a true depth camera, it actually does the green screen.
That's pretty cool.
Yeah.
I didn't know you could do that.
Yeah. Neither did I until I went searching for it. I had a meeting for work. Normally we would all be like in Phoenix or something.
Gotcha.
But I had this meeting, and I was like, okay, well, I better at least be able to share video. And it turns out nobody was sharing video, so it didn't matter. But I 3D printed like a mount that hangs on top of my monitor and holds my phone. It'd be pretty cool if it was actually like necessary.
Well, I mean, you got it set up, and it seems to be working fine. So
yeah, and I mean, it's really cool to have
Worth
a
it.
3D camera. Yeah.
Yeah.
All right. That's good. Do I want to check out the repo in MySys or MSys, or should I just plug it into GitHub Desktop?
We'll check it out in MSys.
Okay.
I think is the easiest way. But it doesn't have Git yet. So the next thing you're going to have to do is install development tools in Git. So if you run that command in your MSys, that will install like all the basic development stuff and the compiler and Git. And I believe that should be the only thing we have to do for like installing stuff. I think you have an A in devel.
Yeah, devel.
And so this will pull in a whole bunch of things, including make and Python and all of that. We could probably filter stuff out from this list, but it's definitely easier to just accept everything.
Yeah. Oh, default is all. Okay, there we go. Yep.
Yep, and now we wait. This is going to take a bit.
It's cool that Python is in there.
Yeah, I wasn't expecting that. There's instructions on the virtual AGC website for setting stuff up in MSys, not MSys 2. But when I followed those instructions, I didn't end up with a working Python. And the script that I wrote to check the bugger words against expected is written in Python. So it was assembling the code, but then failing to check to see if it was correct or not. Oh, so how's it been going?
How's it been going?
Yeah. How you been?
I don't know, man. It's Christmas. I'm doing pretty good.
Nice.
Like, I bought blackout shades for the windows and got them installed in time for Christmas. And so we're going to bed when we're tired and not waking up until we're not tired.
That sounds great.
The only problem is we're out of coffee.
Oh. I mean, I guess the not waking up until you're not tired helps a little bit with that.
Yeah.
But it's still not an ideal situation.
Yeah. I mean, it could be worse. I'm going to go see when the coffee should be here today, but the mail hasn't gotten here yet. Because that's important. Yeah, so I've got a coffee subscription from Blue Bottle, and they're a company in San Francisco.
Oh, okay.
And I actually need to go edit my subscription because we tend to run out right before it arrives. And we've done this for like 3 months in a row. They haven't fixed it. Okay, let's see.
Yeah, just need to
Tuesday.
bump it up just a little bit.
Tracking history. It is not out for delivery today. Okay, so grocery store run is in order. So you're on the West Coast somewhere, right? Where are you?
I'm in South San Francisco, so very close to San Francisco. Not quite there.
Is that where Capella is? Because I kind of would have assumed
Capella's in San Francisco proper.
Oh, okay, cool. Like my assumption is that most of the space folks are down by LA.
We have there's a decent number of space folks up in the San Francisco area. So we're Planet and Astranus. Astra is just a little bit south.
I thought Planet was in Seattle actually, but they're in San Francisco.
Yeah. At least they're last time I checked. I don't think they've moved. Well, I'm pretty sure they're still in San Francisco.
Your memory is more likely to be correct than mine. So yeah, I love San Francisco.
It's a nice area.
It's a fantastic place to visit and spend money.
Yeah.
Not a fantastic place to live, I understand.
It's I like South San Francisco. So I'm kind of surrounded by some nice parks. It's definitely expensive. It's nice being very close to the Computer History Museum. And
I never got to visit.
Yeah, you should definitely go to the Computer History Museum next time you're in the area.
Yeah, I have honestly no idea when I'm going to be back in that part of the country. Because like now that I'm on the East Coast, like when I have time to go travel, and I can actually do that, like it's going to be like New York and Boston and Philadelphia.
Right.
But I mean, my folks are in Southern California, so I'm sure I'll be down there at some point. But that doesn't help.
Nope. SoCal is still quite far away.
So I love San Francisco weather because it's like cold but uniformly cold. What's it look like for you guys right now? Because like keep in mind I'm surrounded by 2 feet of snow.
It has been. I mean, it's San Francisco. Typical winter. It's been like maybe in the 50s or something like that. We've had a couple of days of rain, but not many.
Yeah, I'm actually kind of afraid. It's forecasted to rain, I think, tomorrow, and it's like an inch or two. But with 2 feet of snow on the ground, and you get an inch of rain, it's going to be disgusting. And there goes White Christmas.
Yeah. Also, if it gets really cold after that, it could just be an ice disaster.
Okay. So are we checking out on Git now?
Yeah. So Git clone.
And then it's just virtual AGC / virtual AGC, right?
Yep.
Can I not paste in? Do I have to hold shift? No pasting. Great. Boy, it'd be nice if I could spell it. That doesn't look spelled correctly. Yeah, okay, all right. Maybe I need to get the whole URL. Oh, see.
Yeah, you need the whole URL in there.
Oh, it's git repo clone. Creepo. Jesus Christ.
I think that's if you're using the GitHub official client. It might not work with just regular Git.
Oops. Man, and I really don't have a paste, do I? Oh, there we go. What is it? Shift insert. Fun. Okay.
You have to insert.
Clone. Okay. There we go. There we go. So why is this not actual Git? That seems weird.
What do you mean?
You said if it's not the actual Git command line. Oh, you mean the GitHub?
Right. GitHub provides their own sort of GitHub for desktop thing. And I think the Git repo command only works in that. If I had to guess.
I haven't used the Git CLI in forever. The GitHub desktop is really good. And actually what I've been using recently is VS Code.
Okay, I've heard really good things about that, but I haven't tried it yet.
How do I find my current working directory?
PWD. But it's not PWD.
Yeah.
No.
I had already typed CWD. But this is in a virtual environment.
Yeah. So if you go into the folder where you installed MSys, let's see, MSys 64. I think there's a home folder in there.
Yeah. Yep. There we go. We got.
Okay.
We got a repo.
So a couple more steps. If in the command line you cd into the virtual AGC folder, and then check out the Comanche 45 branch.
Branch Comanche 45 was set up to track remote branch Comanche 45 from origin, switched to a new branch Comanche 45.
Yep, that's what you want to see.
Oh, really?
Okay. And then you need to build the assembler, which you do with that.
That's an awesome command to type.
All right, and then you're going to switch into the Comanche 045 directory with a capital C for Comanche this time. And then you should be able to just type make, and it should build what we have for the Apollo 10 code right now.
Oh, there are HTML files in here. So this is virtual AGC code. Yeah, like the actual like browser emulator, right?
So normally, if you just check out the repository, it's just the .agc files. All of those .html files were just generated when you assembled it. Mm. So the build system defaults to spitting out all those HTML files to make it easy to update the the browsable versions on the website. So yeah, now you're all set up to be able to build this stuff. We're down to, as you can see, we're down to a single bank that is different between what we have and what actually flew. And we know the change that went into that bank, but not how, which is sort of the problem. I guess we can sort of go over, now that we have everything set up, we can sort of go over the issue and how to go about trying to figure it out.
Well, first let's talk about the actual code and the overall structure and maybe a little bit of language as we go on, and we can talk about like it maybe I'd say like nothing specific to this issue. Like, what would you want somebody to know when the next issue comes up or the next issue after that? Like, what fundamental knowledge would somebody need to know?
Okay. So I guess like just basic structure of the code. The Apollo Guidance computer code, from a source code perspective, is split up into a whole bunch of what were called log sections, where the file name for each of these .agc files is the name of the log section that the code went into. And log sections, they were meant to break the code down into like individual chunks. Every log section marked a sequence break for punch card numbers. Usually the first punch card of a log section is punch card number 1. So you don't end up with ridiculously huge punch card numbers by the end of the program.
And so this isn't like
hardware.
It's not like you're importing each of these as a different library, because they're working on the same set of memory, or at least the same half of memory, right?
So the same half of memory,
right? Because the memory is split into 2 chunks, and
that's only from the point of view of the interpreter virtual machine kind of thing.
Oh, okay.
That's a sort of software construct.
Okay.
From the hardware point of view, the code is evenly split between 36 fixed memory banks that are 1,024 words each. And what code goes into what bank is controlled by assembler pseudo operations. You can just say like bank 24 on a line, and it'll switch all the code after that to go into the next available spot in bank 24.
Oh, wow. So it's not even like you have to put each of these, what did you call each of the AGC files?
Log section.
A log section. So you don't even have to keep each log section to one bank. You can skip around and put code wherever you want. Okay, cool.
Yeah. So the code assembles in order, essentially. There's a file that exists in the virtual AGC code called main.agc that was not a real thing back then. That just like essentially sort of pound includes each of these .agc files in the correct order. But when you run all this code through the assembler, it goes straight through in the order that you pass the code to it, and will just start filling out memory banks. So were you to change the order of these files, the assembled result would change.
And how do you know what order they ran them through? If each log starts at punch card 1, how do you know which punch card 1 you start with?
It is all based on the structure of the listings that we have, the printouts from the that actually contain the code.
So
as the assembler processes each line of code, it prints that line out into the listing. Essentially like the physical order of the log sections in the listing tell us what the order was.
Okay, that makes sense. And so it looks like not only are we broken down into different log sections, but you've kind of identified, or I'm assuming it's written down somewhere, each of these log sections gets grouped together into a category.
Yeah, this is getting super nitty-gritty. This is actually a feature that our current assembler doesn't have at all, called subroutines.
Okay.
And subroutines were, nowadays subroutine is kind of like a synonym for function, but that was not really at all the case for Yule. A subroutine is a larger group of, I don't want to say individually assemblable, because they can't really be assembled without each other.
Mm.
But they're individually version controlled groupings of code. So each one of these things like TPC DApps or com erase or com aid, those have their own specific revision on that are stored separately on tape. And then your main program, like if you want to build a new version of Comanche, your main program is a much smaller punch card deck that just has like the description for that program and then instantiates the particular revision of each subroutine that you want.
Huh. That's really helpful. Like, I mean, if you have to work on punch cards and shit, like that seems like that does a lot of work for you.
Yeah, definitely. And it makes it a lot easier to track revisions when it's sort of broken down.
Okay. So each of these log sections contain code that's grouped together, but once it gets, assembled and then actually put into the core memory, it can be wherever, but it goes into a memory bank as dictated by the programmer, or is there a way to just say put this wherever you have room?
There was in Yule the concept of they called them leftovers, where you could say like this constant can go wherever, I don't really care, just stick it, it's a leftover, stick it wherever it fits. As I've never actually seen them use that feature. We just sort of know about it from the listing of the assembler itself. It was essentially all dictated by the programmer. If you look for, there's a log section called tags for relative set locks and blank bank cards. That was sort of like the main file they used to control allocation of memory. So in here, you can see they have block or bank pseudocodes that then have the number of the bank that you want to put those code into, and they don't assign any value to them, but they just assign a bunch of labels to the first address in that bank. And so what they'll usually do is they will do in all the other log sections, they'll do a set lock card, which sets the current program counter to the location of a tag. So like for bank 1 there, they'll do a set lock restart. And that'll set the program counter to the first address in the bank. And then the blank bank card thing is if you just put in a bank card without any bank number associated with it, it'll fast forward the program counter to the first available spot in that bank. So they would define all of these tags here to sort of split stuff up into the different banks, and then use the set lock and blank bank cards to actually do the moving around. So in theory, if they were running out of space in a particular bank, they could just come to this section and shuffle some of these around to get everything to fit. Although a lot of times they would end up having to create new tags.
Okay, why the heck are you guys using tab indentation instead of space indentation?
That's a fantastic question. I hate it very much.
Oh, look! Here's spaces. It's not even consistent. You got some.
Yeah, no, the code in the repository is a disaster of white space. We've done a significant amount of proofing of the non-white space characters. So those are pretty good and pretty accurate, but the white space is all over the place, and some of that stems from trying to make Yayul like behave a little bit more like modern assemblers, and uh, some of it was like changing philosophy over time. Like when Ron first started this project, he was of the mind of trying to clean up the code a little bit. And so he would fix typos that were in the original listing and stuff. And as the virtual AGC project has gone on, the focus has switched much more to preservation and accuracy.
Mm-hmm.
So all the typos, as far as we've been able to do, have been restored and everything. But anyways, the white space has been a really sore sticking point for me for a while, and it's doubly annoying because, like, if you're looking at this file in Comanche 45, the Apollo 10 version, it might be tabs, and then if you go over to like Apollo 8, Colossus 237, there's a very real possibility that it'll be spaces, and like in a very different number of spaces. So you can't really diff the files because they have different kind of white spacing. I've been working on correcting this it very, very slowly. I've been porting, since we got the listing of the original assembler, Yule, from Hugh Blair Smith, I've been working on porting that to Python. And then I have also been working on translating all of our code into actual punch cards.
Oh, yes. That's wonderful.
Which has been a slow process because it's on the order. The big listings will probably be on the order of like 60,000 punch cards each or something like that. But as I go through that process, I'm working on making all the white space as accurate as possible to the listings as well.
So I'm assuming that like these lowercase notes or these lowercase comments are from you folks, and these things which look, I mean, they look like something that was actually written on a, like here's a typo. Is this supposed to be e-cards? No, I guess not.
No. eCatter is erasable complete address. eCatter is an assembler operation that generates a complete address constant for a particular location in erasable memory.
Okay.
But yes, all the lowercase notes, they should be preceded by a double pound sign. The double pound is stuff that we have added sort of in post. So all the page numbers we've annotated with the double pound sign. Also, like anywhere where somebody has written something on the listing, you'll see those. Like there are certain listings, like our Apollo 12 listing has some lines crossed out and other things written in because it was used during Apollo 13 development.
And so which have you decided to include in your source? Do you include everything that's on the page and just comment out the lines that were crossed out?
No, we include the crossed out lines because we want it to assemble to the version that flew, but then we make a note next to that line saying this line was crossed out and they wrote this in the margin next to it.
I see. Okay, that makes, yeah, gotcha. Okay, so so if main.agc is a fake file that you've built for your virtual assembler, tags for relative set lock and blank bay cards seems closer to the equivalent that they would have used. Is that fair?
Yeah, more or less. The equivalent. I don't even think that we transcribed this section. Let me find it. There's another section just called subroutine calls that instantiates each of the subroutines that you want. And that's more or less the equivalent of our main.agc.
pinball noun tables. God, I love some of the variable names that they used, and like the Burn Baby Burn program or a subroutine. Like
there's so much good stuff in the source code. One of my favorites, and it's stuff that, I mean, I don't know. I haven't seen the code for like major NASA missions, really. Other than I've seen a little bit of the Laddie flight software, but some of the stuff, I can't imagine that I can't imagine it would fly at the major contractors nowadays. Program 00, like the main idling program, they called that poo, right? So when you go back to the idling program, the common way to refer to that is to go to poo. But there's a particular abort routine where, in the case of a software abort, where I think this is actually the one that happened on Apollo 11, like the routine that got triggered on Apollo 11. Like when you're in a major software abort scenario, you need to go back to the idling program because everything is screwed up.
Right.
I guess they didn't go back to poo on Apollo 11. They kept going. Anyways, so in that situation, you want to flush out the whole system and go to poo, right? And so how do you force a poo? You call the routine enema. And it's just, yeah, the code is completely filled with stuff like that, where you're reading along and then you hit something like that, and it's like, oh man, that's wow.
I mean, they had a median age of what, 24, 25, like.
Yep.
Okay. So, to go back to the structure of the program, so we can kind of think about each of these logs as libraries that you're going to import, kind of. What are the other main structures that we should look at?
That's a good question. I feel like we've really sort of covered most of the main structure here. Hold on, let me find this page really fast. Erasable assignments. That's main. I'm almost there. Here we go. So that is the page that I was referring to in the listing. It's a small log section in the main program that is, it just says subroutine com-erase pull intervision 30, subroutine com-aid pull intervision 29, and all of that. And so that set of subroutines defines the Apollo 11 code in this case.
So somebody, I'm going to assume fairly high up, typed up this page on a typewriter, and then they would have handed it off to a computer, and they would have turned this into a punch card, and then put the punch card on top of the stack of punch cards that they were putting into Yule, or what happens? Like what actually happens with this?
So once you have an AGC program assembled for the first time, to further revise on it, you only have to pass in punch cards that describe changes from the previous revision.
At a per line level, not even at a per log level.
Right. So because the log sections are sequence breaks and restart the punch card numbering, there is a special type. They had several sets of what they called merge control cards that controlled how your inputs were merged with what was coming in from tape. So there was a type of merged control card called the acceptor card, where you would type on the punch card equals log and then the name of the log section, and it would fast forward through the listing or through the program as it assembled until it hit that particular log section. And then after that, you just typed the punch card number that you wanted to change and then the new contents of that line. Or you could punch a punch card number that goes in between two existing ones, for example, to insert a new line of code. Or you could type the existing punch card number and then delete through, and then add like an ending number, and it would delete all of those cards. So in the case here where they have specific revisions listed, they would have just said, okay, equals log subroutine calls card number 0001 subrow comma race 30, and it would go into what had been stored on tape previously for this program and replace it with that line to bump up the revision number for that subroutine.
Oh, and it would edit the tape.
Yes. Yeah.
Oh, okay.
So,
okay.
So this would then be stored on tape as revision 55, okay. And then when you go to assemble revision 56, it pulls from the previous revision.
Okay. And they were rewriting the same tapes over. It wasn't like for each revision, they took that whole set of tapes and set them aside and then copied over what they needed for the next revision. They were just directly editing into the production branch, as it were.
No, I don't think so. They didn't do this for the branches, which we can talk about in a bit, but for all of the mainline programs like Comanche revisions 51, 52, 53, 54, 55, as far as I know, those were all stored on tape or on disk, and you could command the assembler to the operation was called reprint, but it was really reassemble. You could reprint any of the main programs at any time. You could also do assemble new revision of Comanche 55, or assemble new version of Comanche 55 as, Batman or something, and it would create a new program with the contents of that particular revision that you could then go off and edit. And so that came in handy in a lot of the flown programs where they either were directed by NASA to add features later, or they found like a critical bug that they had to go back and fix. So like in the example of Apollo 10, they had released Luminary revision 69, and then meanwhile had been working on Apollo 11. And I think they got up to like revision 97 or something like that. And then they got directed by NASA to add a different gravity model for the moon to the Apollo 10 code. And so they created a new version of Luminary 69 called Loom 69, and then revised that up to revision 2 to add in the new gravity model, because they had not completed testing of and didn't want to completely change out all of the other things for Apollo 10 that they had been, they'd gone through the flight software readiness review and everything for.
That's pretty cool. Like, and they were making this up as they went. Like, I can't imagine. So like, a friend of the show, Chris Radcliffe, he writes code for Blue Origin, but he only writes code for their internal software management. He doesn't write any flight software. It's just utilities and productivity tools. And
nice.
That's fantastic. And he's a productivity multiplier.
Yeah, for sure.
But like, he has a lot of material to build on and like lessons learned to employ. And I can't imagine writing flight software when nobody had written anything that was anywhere near this complex, or flexible. I mean, flexible code
Right.
is fantastic, but it also brings so many additional issues. And I can't imagine writing that code. I can't imagine coming up with the policies and utilities that you would need to manage that code. It's insane. Okay.
Yeah.
Oh boy, my brain is struggling to take all this in. This is just so much good information. Okay. So let's talk about the actual language, if you don't mind.
Sure.
What? Why don't you give me an AGC file to pull up, and we can talk about the actual syntax of the language.
Okay. Let me find a good one. Let's see. Um, the
And
reason
also,
why I say a good one is because when you're coding for the AGC, you're writing in two different languages depending on what you're trying to do.
oh, okay.
Um, let's see here. Which one would have good examples of both? Uh, let's see. No. Maybe this one? No. Let's see. So I guess while I'm looking for a good file, I can start talking about that. So a lot of the code in the AGC is just written in its native machine language, which they called BASIC. It doesn't have any relation to the BASIC that most people know, like Visual Basic and all of that.
And
Um,
I feel like Basic actually wasn't that long after Apollo, right?
yeah, I don't think it came that long after. But
64.
yeah, there's no relation there. Basic just means the um,
1964.
oh really? Okay.
Yeah,
So they did overlap by quite a bit,
yeah.
and I guess either it wasn't widespread enough, or they just didn't care.
They probably just didn't care. This was never going to run on the ground. I mean, you know what I mean. Like it was never going to be in a situation where you had to worry about actual Basic being around.
Right? Yeah. Okay. So let's look at P11. This seems to have a decent mix.
Yeah, I actually have P11 open already because I don't have P00. It starts at P11.
Yeah, P00. The programs are uh, like the numbered programs are more of a formality grouping of jobs running in the computer. They don't really mean a whole lot, other than just sort of like an indicator to the astronaut that these are more or less the jobs that are running at the time. There are
Yeah.
some things that check the job number, but mostly it's just this set of jobs starts and they set the display number to 11, and then they just continue on and do their thing, and that's all the 11 really means.
Okay, so here we have P11 through. It looks like the highest one is P76, and so these are, like, you actually run the programs while you're in flight, and depending on what phase of flight you jump between programs, and
Mm-hmm.
so are they gonna? So it's almost like the major program files are the the main loop or the top level code, and then from there they're referencing all of the other logs as if they were libraries with utilities that you want to use. Is that fair?
Yeah, more or less. It's not that cleanly divided.
Sure.
Like the main programs for the lunar module, the landing programs, those are all P63, P64, P65, P66. Those are all on a log section called Lunar Landing Guidance Equations, or the Lunar Landing.
So
there,
why
there,
do
are,
they call
there are plenty of
P11?
other programs in the command module that are not like cleanly listed in these P number files.
And so that's like clearly not even just to make it easy for the astronauts to put the computer into a particular program. So why didn't they name, in this case, P11.AGC, but why didn't they name the P11 stack of cards Earth Orbit Insertion Monitor Program?
It probably just came down to the personal preference of whoever created that log section the first time,
okay,
honestly.
Yeah, fair enough. Fair enough. Okay, so this starts out with a function string. Like it's actually really nice documentation. It tells you who can, where P11 will be initiated, and then I guess where it says program will, and then we have a bunch of numbered bullets. This is sort of a walkthrough of the major functions of P11.
Yeah.
This is so nice.
They definitely they put a lot of effort into making the code as self-documenting as possible, and really filling out all of these remarks cards, as they called them, to describe what is going on. Some people were definitely better at it than others, and it kind of, as far as we can tell, how good they were at updating these comments sort of came in waves. There are some times where they were super good and made very clear all the changes they were making, and then sometimes there would just be a whole bunch of code changes without any common changes. And some of these descriptions up at the top here, there were places where it's out of date and doesn't really exactly reflect what the code is doing anymore.
Oh, that's worse than not having anything.
Yeah. And then there are sometimes, like right after Apollo 14, they went through and just did a couple of revisions of the code where all they did was update comments. So it's a mixed bag, but for the most part, it's really good and helpful.
Okay. Well, P11, I don't know if it's accurate for this revision, but it looks great. If astronaut has requested any of these displays, he must hit proceed to return normal noun 62 display normal. Man, like, yeah, this is such. I have seen modern day repos that aren't as well documented as this. Okay, so I guess on line 136 or so is where we actually start the code, because we've got count 34/P11, and is. Well, I guess that wouldn't be where card 0 starts, right? So what's count 34/P11? Is this just comment, or does this actually get compiled into actual code?
It is, that one is a directive to the assembler. So that's saying for all of the code that follows, count up how many words there are and put it into the 34/P11 grouping. So this was sort of a feature that they added to the assembler as they started to run out of memory, and started to have to really figure out where all of the memory was going to try to identify things to get rid of. So at the very end of the listing, there is a special table that the assembler prints out that just says, okay, 34/P11 has 127 words in it. 34/P20 has this many words in it, and it has the sum for each of those little sections, and then the cumulative sum so far. And at the very end, it prints out statistics about, okay, this is the total number of words in the program. There's this many words remaining. So that's sort of just like a directive to help with the memory management.
Okay. So the address 34 has nothing to do with the AGC. It has to do with Yule's environment.
The 34 there implies that all the code that follows is going to be in bank 34.
Oh, okay. Okay.
And they would have had, because of the way that particular line is written, they would have had to update that card to change the bank number in it if they changed the bank that all the code was going into. There was a different version of that pseudo operation, count star. If you put an asterisk after it, you can then do ** /P11, and it would automatically fill in the bank number that you're in.
Okay.
But I think that was a later feature, and this code was probably written before they had that.
Okay, cool. So I'll let you run it from here, because you know what a good way to approach this would be.
Okay, yeah. Well, I mean, so the very next line, so I guess the immediate next line is just defining one label to be equal to another. So they're saying bits 5 and 6 are equal to super 0, 1, 1, which they're doing there just to save memory. They don't want to redefine constants if they don't have to.
Okay, so super 011 was defined in an earlier log section.
It could be in a later log section too. The assembler is pretty smart about resolving things. Okay. But that is just a variable that happened to have the value that they wanted for bits 5 and 6.
Okay.
But the next line after that is clearly a lie, because we were just talking about how all of this code is going to be going into bank 34. So the whole using setlock followed by a blank bank card was a strategy that they settled on later for moving chunks of code around. Originally, they would just use these straight bank number cards. And at some point, we could probably figure out exactly when they did it. I think we might have enough code now to be able to sort of pinpoint that down. But so at some point they changed their strategy, and when they did so, they weren't particularly good about going through and deleting all of the original specifically numbered bank cards. So that bank 42 card briefly sets the current bank to 42, and then the setlock P11-1 bank presumably then sets it back to 34 for all the stuff after to go into. Okay. So after that, there's another pseudo operation for the assembler, an eBank equals card. So just like the program memory is split up into 36 individual 1024 word banks, your RAM or your erasable memory is broken down into 8 256 word banks. So eBank equals tells the assembler what the current bank is for this code that you're about to write, what the current erasable bank is. And for that, you just specify any variable in that bank. So TFM, the ephemeris time, is some sort of variable, or is a variable in the bank that they want. So they say eBank equals TFM. And then after that is where the actual code for P11 starts.
So wait, so you're saying TFM, and I'm saying TFEM. Are you saying TEFM? Like what? How are you pronouncing this? And do you know what that variable might be a contraction of?
Yeah. It's T. You can think of it as like T sub FM. It's an ephemeris time.
Oh, I see. TEFEM. I see. Oh,
yes.
Okay.
Yeah.
Okay. Okay, that was hurting. Okay. Okay, so they're referencing, TFM. Okay. And so when you're saying, like you called this an eBank card, so does that line go on its own card?
Yes. Yeah.
Does each line get its own card?
Sorry?
You don't need a single card for every single instruction, do you?
Yes.
Oh, I guess that makes sense because the punch cards were binary, and so while this is 2 words and an equal sign, to actually turn that into a punch card, you need a lot of holes, right?
The punch cards were they weren't binary. They were it's essentially like a line of code. There are 80 columns. So column 1 is dedicated to the type of punch card. So a normal line of code just leaves that blank. A comment line will have an R or an A or a P, depending on how you want that comment to be formatted. A new log section will have an L in column 1. And then columns 2 through 7 are the punch card number. Column 8 is the vertical spacing. So if you want a blank line after the current line, you put a 2 after, or in column 8. If you want 3 blank lines, you put a 4 in column 8. If you want to force a page feed, you put an 8 into column 8. And then columns 9 through 16 or something like that are the label. And then there's a set of columns for the instruction, a set of columns for the address for that instruction, and then a set of columns for the comment.
Man, okay, all right.
So if I say card, I really just mean like a line of code.
Great.
They're pretty much equivalent.
And the leading indentation, what is that indicating to us? Because my initial assumption was that cards began with no indentation, then everything indented under that was on the same card, but clearly.
So the indentation, it helps more to think about it as just different columns within the card. So the leftmost column, as seen in the code here, is the label to be associated with that address if you want to give it a name, like if you want to name your function something. And then the second column is instruction opcodes, and the third column is addresses that those opcodes operate on.
Okay, that makes sense. Okay, so now I see actually there are a couple of P11s here, but okay. Okay. So we're naming this next card, we're naming it P11.
Yes. Yeah, so this address is called P11. So any other function can call P11, or they can jump to P11 and it'll come here. And P11 is starting out here with actually changing the erasable bank to the one it wants. So it's doing CA, which is clear the accumulator and load it with a value. Clear and add is what that stands for. It's loading the ebank3 constant, and then TS, transfer to storage, is putting it into the ebank register, which is what controls the switching of erasable banks. So then it goes on from there. So sets up restart protection next, and then.
Well, so TS on line 143, it's referring to P11 from the previous card?
No, that's just the next instruction after the location that has been tagged P11. So these are one instruction at a time. So the first instruction executed in P11 would be this clear and add, and then it does after that it moves on and does this transfer to storage instruction. And
so what is it going to be transferring to storage? What, the variable ebank?
Yeah, so the first line,
which is
CA
TFM.
ebank3.
Okay.
Ebank3 is a constant in fixed memory that has the particular setting of bits that you want to put into the ebank register to select erasable bank 3. So the first line loads that constant into the accumulator, the A register, and then transfer to storage on the next line writes the contents of the accumulator into ebank, which in this case is a hardware register that switches which bank you have. So generally speaking, with the AGC is it's an accumulator-based computer. So almost every instruction implicitly modifies the accumulator somehow. So if after this CA ebank 3 there was an add instruction, that add would have it would have another address, say 2. So you could say CA ebank 3 add 2, and it would then, the add instruction loads the value of the constant 2 and adds it onto the accumulator, which you loaded in the previous step.
Okay. So there are going to be a lot of accumulator clears whenever we're done. Oh yeah, like even on 160, I see CA0. So it's kind of like emptying out your pocket or wiping off your whiteboard. Okay.
Yep.
Okay. That makes so much sense. I was like, all right. Okay, so what's extend?
Oh boy, extend. Okay, so the extend is a really interesting hack that they came up with to double the amount of instructions the AGC had. So the Apollo guidance computer, the Block 2 Apollo guidance computer, has 15-bit words, where 12 of those are needed to specify an address, and they only have 3 bits left over for the opcode. And 3 bits for an opcode gets you 8 different instructions that you can have in the computer. And yet they managed to put in 40-something using various hacks. So extend is one of those hacks, where if you execute an extend instruction, the next instruction is selected from a secondary set of operations.
Okay.
So in this particular case, CA and DCA are both opcode 3, but the fact that there's an extend before the DCA makes the computer execute it as DCA instead of CA.
And so why was extend written in there? If you already are saying DCA, why doesn't why doesn't the assembler know, okay, I need to extend and then go to this command?
That is a really interesting question, and I've never really thought about it before. The assembler definitely knows. That would be a really interesting question to ask to Hugh, and to see what he says about that. It may have just been for the clarity, I guess.
Mm-hmm.
To make it clear that you're switching the set there, and that instruction assembles to 2 words, or the extend is its own word in memory. So to make it clear that you're using 2 words for an instruction there instead of 1.
Yeah.
There are a couple of places where they got very, very clever and abused the extend, and sometimes executed the same instruction either with extend or without it.
Lovely.
Which is super dirty, and very, very clever. If you haven't read Don Iles's book Sunburst and Luminary, the biggest example of that, he talks about coming up with that and presenting it at MIT, and everybody's saying, there's no way this will possibly work. What are you talking about? And he was like, it does work. Try it out and see.
Jesus. Okay. So
it's a very good book. I highly recommend it.
I don't have that much time for reading, but I'm going to put it in my list anyway, and eventually one day I'll get around to it. Okay, so DCA, I'm assuming, is direct clear add, maybe?
It's double clear and add.
Double clear.
So in addition to your A register, the accumulator, there's also an L register, which is the lower accumulator. So the AGC has a limited set of double precision operations that it can do. So DCA loads a double precision number into the accumulator and lower accumulator.
Sorry, hang on. Reggie, stop that. Come here. Come here. That's enough. That's enough. Quiet. That's enough. Oh, good boys. Ags, come here. Aglet, come here. Aglet, come here. Look at what. This is why we haven't killed the dogs yet. Because they're just super adorable. Okay, so you have the lower register, and then what's the normal register called? I missed that.
Just the accumulator.
Oh,
so you have the A register and the L register.
Okay. And so the L register was used for double precision.
Yep. Largely
which
speaking. So yeah, you can do a double load into it. If you do a multiply, like multiplying two 15-bit numbers together, you could potentially end up with a 30-bit number. So when you do a multiply, the result is sort of split between the A and L registers. And then similarly for divide, when you do a divide instruction, you're expected to have a double precision number in A and L, and then the result will be an A, and the remainder will be an L.
Okay. So it's clearing both registers and adding rep 11s.
Yep. Rep 11s in this case is going to be a not a double precision number, but probably a 2-catter, which is a 2-word complete address, which is enough information to completely specify a location in memory and then both the fixed memory bank and the erasable memory bank associated with it. So what they're doing in this little block of code is they're changing their restart protection to go to a particular location if the computer suddenly restarts. So they're saying, okay, so rep 11 is where you go now if you restart. And rep 11 is P11, redo P11.
Oh, I see. Okay, and so that variable, hey, here's where you're gonna here's where you're gonna restart at the beginning of P11.
Mm-hmm.
That's being stored in the accumulator.
Yep.
So now we can't touch the accumulator for the rest of this restart protected block of code.
No. So actually the very next line after that DCA is a de-exchange with minus phase 3. The phase variables are the restart table. So all of those describe what the computer does on a restart. So they're changing the phase. De-exchange switches the contents of A and L with 2 locations in memory. So they've loaded this P11s, and then they are doing a de-exchange on minus phase 3, which puts what's in A and L into minus phase 3, and then loads minus phase 3 and minus phase 3 plus 1 into the accumulator.
Yeah.
They didn't. The reason they're doing an exchange here is just that they didn't have a double precision store instruction, and they didn't care about what used to be in minus phase 3. So they're loading it and then getting rid of it immediately.
So CA is clear and add. CS is clear and I see, clear and store. So instead of adding,
okay. You were close. It's clear and subtract.
Okay. So you could CS there could be CA and it doesn't matter.
No, it does matter because the Apollo guidance computer is a 1's precision computer, and positive 0 is not equal to negative 0. So their CS0 on this line is CS loads the complement of whatever you specify into the accumulator. So they're loading the complement of 0, which will be negative 0, into the accumulator there.
So what 1's precision, I've heard this term, I think, on number file, but I completely forget what it means. So it's an alternative to like a signed integer. Is that right?
It's a different way of storing signed numbers.
Oh, okay.
So the 2 ways of doing it are 1's complement and 2's complement. For 1's complement, all you do is you invert all the bits of your number. So all the zeros become ones and all the ones become zeros. And that's how you do it. So positive 0 would be encoded as 0, 0, 0, 0, 0. Negative 0 would be encoded as 1, 1, 1, 1, 1, 1, 1. But that has the downside that you have these two different values for 0, which doesn't really make any mathematical sense. And so 2's complement solves that. And the way you encode negative numbers with 2's complement is you invert all the bits and then you add 1. And that works out such that the two zeros both converge to 0.
All right, I am way over my head. I have no idea what you're talking about at this point.
Sorry, probably not doing a good job describing things.
No. That's I'm sure you are. I forgot some of the basic things here. Okay, so unsigned values. Okay. So one's complement, you define a negative number. Right. So instead of 0, 1, 1, 1, 1, 1, 1 to get 120, or instead of 0, 0, 0, 1 to get 1, to get negative 1, you do 1, 1, 1, 0. So how do you know that 1, 1, 1, 0 in one's complement? How do you know that 1, 1, 1, 0? Well, I mean, I'm dropping the 4 ones, but how do you know that that's not what, 254?
It's essentially context specific. That leading 1 is considered to be the sign bit. So usually
oh, so you're just cutting your numbers in half and putting okay. Yeah. All right.
Right.
So one's okay.
You don't have to do that. You can use it as an unsigned number and have all 15 bits. But if you're doing math, it's normally you have the one signed bit and then 14 bits of data.
And AGC could do both modes, an unsigned and a ones complement, or it was just ones complement?
They're equivalent. It turns out it's really just context and how you use the numbers. Mathematically, they're the same.
Yeah. I mean, that makes sense. It's just how you, yeah. Jesus. Okay. So we've stored rep 11s into phase 3, and then we've loaded up -0 into the accumulator, the A accumulator.
Yep.
And why was it important to have negative instead of positive?
Let's see. So they're storing that into lift temp. I haven't really gone through command module code a whole lot, so
it's okay if we just say it's important for another bit of the code. That's okay.
Yeah, I think actually. Oh no, I see what they're doing. So if you follow along, if skip over the transfer to storage to lift temp, they clearly wanted -0 and lift temp for some reason. But the next line after that is de-exchange minus phase 5. So they had a little bit of safety built into their restart tables. They wanted to make sure if the computer restarted and the restart tables were complete garbage, that the computer didn't just go off and do something that it shouldn't do. And so the way they sort of verified the integrity of the restart tables was they any data they put into them, they stored both negative and positive. So negative phase 5 gets the negative of whatever you're putting into the restart table, and then there's another variable that's just called phase 5 without the minus sign that gets the positive equivalent to that variable. And when the computer restarts, it loops through your restart table and makes sure that it's all internally consistent, that the positive variables are in fact the opposite of the negative variables. And if not, then it just throws out the restart table, says, I don't know what to do, and goes to program 00.
Even if one of them is wrong?
I think so.
Okay.
I'm not completely sure, but I think so.
What a garbage way to do fault protection, because you have to double the number of addresses that you're eating up, and you can't even do any error correction.
Oh yeah, there's definitely no room for error correction or anything like that.
I mean, but if you don't care about error correction, then why even? Okay.
You don't want it to suddenly decide to fire the engine, right? If you have corrupted memory there.
For sure.
So it's much better to just throw everything out and go into a safe state.
And I guess that's the only absolutely sure way to know that there's been an error somewhere.
Right. Yeah. If you only have to store the number once, it's entirely possible for it to have just gotten garbage written to it.
Okay, so we stored -0. I don't know what ZL is.
But 0, the L register.
Oh, okay. Yeah.
So that's putting +0 into L, and then they're doing a D exchange on -phase 5. So that's setting -phase 5 to -0 and phase 5 to +0, which makes them internally consistent in the restart table.
Okay. Do you happen to know off the top of your head what the different what the difference is between like phase 3 and phase 5? Like, because I can understand putting rep 11 into phase 3. That must mean that phase 3 it points us back to where we're going to start. Do you know what phase 5 did? Because this is inactive group 5.
So that's just shutting off whatever might be in group 5. There is another there's another file if you look for restarttables.agc. That is sort of a list of all the things to do for different phases.
Phase of flight. Okay.
Yeah, more or less. The leading number for all of these different spots is like the controlling phase number. So the 5 dots will be associated with the phase 5 and minus phase 5 register. And then the number following that is the action taken for that particular number. So by putting 0 into phase 5, they're essentially shutting off any one of these particular responses that may have been active previously.
Okay, cool. I understand enough. Okay, and then we're going to do P11 plus 7. Does that mean P18? Or does that mean a subset of P11?
So this is sort of like just a fun fact for assemblers from the 60s. You can use whatever characters you want in variable names because it's all column based and it doesn't do any math internally. It doesn't matter. You can have plus signs, you can have parentheses, you can have numbers leading. So P11 plus 7 is just a different variable name. Okay. In this case, the label for another function.
Okay, and then we have an extend after that, and then another DCA, which is where the extend comes from. Why is extend on the same card instead of on the next card?
So the labels have to be associated with some instruction in memory. So it wouldn't really make any sense to just have the P11 plus 7
right.
And then nothing, because you're not really associating it with a particular location then.
Okay, so this is just saying at some point if you need to come back to P11 plus 7, you're going to start by extending and then doing this DCA.
Yes, yeah.
Okay. And we get another rep 11, but now it's not rep 11S, it's rep 11SA. Very
creative variable naming there, yeah.
Yeah. So I guess I don't know what the S in rep 11S means. It's just
let's see. Rep 11SA. If you search for that, these are constants defined sort of in the middle of the file, and they are just straight octal constants, which It looks like they're double precision octal constants. It looks like they've just sort of hard coded the negative positive sort of thing for the restart tables. So rep 11s it starts out with 77766, which is negative octal 11, and then they follow that up with positive octal 11, and then same for rep 11 SA, except it's 13.
Okay, fair enough. Okay, so we go and grab. Well, so it's an exchange, right? DCA is. Oh no, that's not DXCH. So.
Yeah, so okay. DCA is just the double precision load, and then you're using the D exchange to store that into a particular location.
Okay, and so I guess right. Okay, so we're putting rep 11 SA into T liftoff, and then now our register has whatever was in T liftoff, but it doesn't matter because we're going to go and load time 2.
Yep.
And then put that into lift temp.
Okay. Yep, you got it.
And then we clear CA is the upper.
Yeah, so that is only doing the A register.
Okay. And so it's clear and add. So we get positive 0, and then the lower register gets a positive 0 as well.
Yes.
So why is it CA and not just ZL or a ZA, I guess?
They could have. Okay. I don't have a good answer for that one.
That's okay. Okay, so then we put as many zeros as possible into time 2.
Yeah, I'll be right back. I'm gonna take a quick bathroom run.
Oh, yeah.
All right, I'm back.
Welcome.
Oh.
Okay, and then
yeah. So the ZL thing is interesting. There's a particular location in erasable memory at address 7 where the hardware just returns zeros to you no matter what. And ZL hits that. It's doing a load into the L register from that hardwired 0. But when you see 0 spelled out, that's a fixed, that's a 0 constant stored in fixed memory. So I'm not really sure why they bothered to have a 0 defined for fixed memory when there was a dedicated address that always gave you 0. It seems like they could have saved a word there. It may have just been, one of those things where
the computer architecture was slowly changing over time through the Apollo program. So it may have been like just the different time periods at which things were introduced.
I mean, yeah, it makes sense. Okay, so then we've got two labels here that are pretty similar. And so I'm assuming that these are going to be like, because they're labeled, it means that we can come back to them easily later.
Yep.
So these get you, like, I guess. So I know we already set T liftoff and we already set phase 3. So at some point we'll need to come back and grab one of these two, but why? What's the point of de-exchanging to T liftoff and then immediately doing the same? So it's moving T liftoff into phase 3.
Yes, yeah, that's what that is accomplishing.
Okay. And sometimes, presumably at some point in the program, we're going to want to be able to put something else into phase 3 instead of T liftoff.
Yep, you got it. And it looks like if you go down, there's a little function called end rep11 that does, or no, it might just be re11. No, yeah, it's end rep11 that does exactly that.
Oh, really? And like it would be in the first column, right?
Yes, line 388, I think.
Okay. So I chickened out before I went. Okay. And rep11. Okay. So it's going to extend DCA, rep11, SA, TCF. Oh, TCF must be jumping to a line in code then.
Yes, TCF is transfer control to fixed memory. There's two unconditional jump instructions. TCF does not set a return address. TC stores the return address in the queue register, so you can go back to where you came from.
Oh, cool. Okay. What were those two again? So TCF doesn't save your place and TC does?
Yes.
Okay, cool. Yeah, and that, like, it's funny that you said non-conditional because, like, yeah, it's kind of crazy. Like, if you have 3 columns and one of them is a label, yeah, you can't really do conditionals in the way that we think of them today.
Yeah. Let me look at, let's see, where are you? If you look at rep11, we can talk about one of the most interesting instructions in this computer.
Yeah, so back down like the 380 somewhere. Okay.
Yeah, 367, I think.
Oh, rep11 is 350.
Okay, I think we're looking at different versions of the code.
Okay. So rep11 is the one that starts with inhint, right?
Yeah, inhint is inhibit interrupts, so that just stops any interrupts from being processed until you do a relent to release interrupts. The next instruction after that is the really interesting one.
So real quick, I'm familiar with the idea of interrupts, but in this case, they're not talking about external sensors or something doing an IRQ. They're talking about another subroutine asking to take over the processor and do something.
No, you're right the first time. It is IRQs essentially.
Oh, okay. And I guess
so those could be either from like timers, internal timers, but there's also IRQs dedicated to like the hand controller for the astronauts and the PCM, which was the box in the spacecraft that handled sending telemetry to the ground, could generate an interrupt in the AGC saying, "Hey, give me more data to downlink."
Oh, okay. And those interrupts are defined in software somehow?
Yeah, when the AGC takes an interrupt, it jumps to a specific address. So there's a file, there's a log section called interrupt lead-ins that assembles handlers for those IRQs to those specific addresses.
Okay, so they weren't set dynamically. They were set ahead of time.
No, yeah, they're hard coded.
Okay. Okay, that's good. Okay. All right. So rep 11 starts with inhint.
Yep. So inhibit any processing of interrupts until it releases those.
Okay. So we're going to do something important here.
Yep. Yeah. This is all. Don't interrupt me. And then the next instruction is CCS. And CCS is a monster of an instruction. And to understand it, you have to sort of understand where it's coming from. You talked about this with Hubler Smith when you had him on, but the AGC was born from the Mod 3C Mars computer, which was a very, very tiny computer, much more restricted than the AGC, and it only had, I think it only had the 8 instructions. And so designing instruction sets for computers at that time was really how can we pack the most functionality into the smallest set of instructions? And so for an example of that, the clear and add CA didn't exist originally. It used to only be CS, clear and subtract. So you could only load the complement of numbers. You couldn't load the positive version of it, which led to all sorts of interesting gymnastics.
Yeah, so I guess
and if
there wouldn't have been a clear and complement that you could do afterwards, where you right.
Yeah, so that was sort of the thinking, and that like if you absolutely needed to have the positive version of that number, you could do clear and subtract of your number in memory, and then clear and subtract the accumulator itself to flip its sign around. But generally, they tried to just deal with the numbers changing signs every time they accessed them. So CCS is an instruction born of this very limited instruction mindset. It stands for count, compare, and skip. And so what it does is it loads the variable in its address. So in this case, it's loading phase 5. And then based on the value of phase 5, if phase 5 is positive, it executes the next instruction. If it's positive 0, it skips to the instruction after that. If it's negative, it skips 2 instructions. And if it's negative 0, it skips 3 instructions. And then once it's determined where it's going to jump to, it then takes the absolute value of the number and subtracts 1 from it, and then stores that into the accumulator. So there's a whole lot going on with it.
Holy cow. Okay. So it's going to use whatever's stored in phase 5 to determine how many lines it's going to skip.
Yep.
And it's going to skip lines here in this sequence of instructions?
Yeah. So in this case, it looks like they've just sort of implicitly coded this under the assumption that phase 5 can only be positive or positive 0, because the negative slot, they just have another unrelated CCS that they probably don't want to skip over. And that was it's sort of a thing that especially in modern flight software, you would never get away with making an assumption like this. But for them, the way they did it is, if they could prove that number should never be positive, or like if they can prove that number should never be negative, then they can code assuming that it's not. So in this case, they're only using the positive or positive 0 slots for the CCS to say, if phase 5 is positive, then go to end of job to stop the currently running job. But if it's positive 0, then let's go check lift temp. And in this case, they're not actually using the absolute value and diminishing of the accumulator. They're just using it for the branching.
Okay. And so TC, it allows you to jump back, right? Which,
yeah.
Why would that be TCA if we're going to an end of job routine?
It doesn't matter at all. You'll see TCF just as frequently as TC to end of job.
Okay. So just pick one and go, because end of job doesn't care.
Yep.
So I guess, do you know what would have been setting phase 5 before we got to this point?
So we're in repeat 11 now, which was set up as a restart point up at the main entry point P11 that we were looking at. So what was set to phase 5 up there? Let's see. So it's directing restarts to repeat 11, and then it tries to inactive group 5. So it's possible that a restart could have happened before or between the setting of phase 3 and the setting of phase 5. So it could be looking for that to see if the restart happened there. Or it could just be that P11 uses phase 5 for other things. And it's looking to see exactly which phase it's in of phase 5 if it's non-zero.
Okay. So if we were to skip over end of job, we do another CCS. So we're going to check lift temp, and when that happens, we're going to TCF to one of these variables, I guess.
Those are all relative TCFs. So if you didn't give a variable name, you could just say TCF to one instruction after this one. So the current location +4 or current location +3.
Okay, so this +4, 1, 2, 3, 4 would be T liftoff. This would also be T liftoff. This would also be T liftoff. So it's saying you've got 3 options that are gonna get you to liftoff, and then one jumps you to P11 +7, which we saw earlier.
Only in the -0 case it goes to P11 +7.
Okay, so it's positive, +0, -0, negative.
Positive, +0, negative, -0.
Oh, okay. Like, there's so many things that you just, like, come on, guys, make it easy. It's incredible the amount of hoops that humans have jumped through in early computer science.
Yeah, it took me a very long time to really internalize all of this.
Yeah. Okay. So, depending on what lift temp is, do you know what lift temp is off the top of your head?
It got given a -0 at the beginning. I think we were talking about that during the restart protection stuff.
Okay, so it's not a sensor
ZL,
reading.
TS lift temp.
So it's temp as in temporary, not temp as in temperature.
Correct. Yeah.
Okay, so that's some sort of flag that's going to tell us whether we can copy and subtract T liftoff, or whether we will, what is it? Go to P11 +7, which is it's the restart code that we were looking at.
Yeah. So BZMF is branch if 0 or minus. So that's a much more clear sort of comparative jump. So it's taking the negative of T liftoff there and then extend BZMF. So if the negative of T liftoff is 0 or negative, then go to end repeat 11. Otherwise, keep going.
Okay. Okay. And then we do another CSS for time 2. That must be a global time if it says it's something that must be non-zero at liftoff.
Yes, time 2 is a hardware timer that just starts counting up when you turn on the computer.
Okay. So why would time 2 ever be 0? Like, how would this code execute? How would this instruction execute so fast that the timer hadn't even ticked once?
So the answer to that is time 1 and time 2 make up a double precision timer, where time 1 is the lower 15 bits, and time 2 is the upper 15 bits. And I think it rolls over in either the single or double digit seconds, I think, is when it rolls over. So it's definitely possible for time 2 to be 0 within a few having the computer turned on.
Okay, so it must be non-zero at liftoff. So if it is 0, then would we jump down to this line or to the blank line on 366 or the extend on 367?
You can ignore the blank line.
Okay.
So it would be jumping down to the extend.
Okay. And right, so if it's positive, then we'll TCF rep 11A.
Mm-hmm.
And what's the -5? Is that telling it how to get back? Or is that just passing along a number to... No, I have no idea what that is.
That is... so that is a modifier to rep 11A. So what's actually being encoded in there is 5 instructions before rep 11A. So if you go to rep 11A and then count up 5, that's where that's actually going to jump to.
Yeah. That makes... Okay. Yeah, we are...
So it'll be to the CA0 up there.
Okay. And so that will clear out at least time 2. Okay, cool. So CSS time 2 must be non-zero at liftoff. So if it is 0, we'll go to extend. If it's positive, and so time 2 would never be a negative number or a -0. Okay.
Right.
So if it is 0, or if it's... So if it's positive, we'll go clear. It says T2 and T1, but I only saw T2 being cleared. But
was it a D exchange? In memory, time 1 immediately follows time 2. So a D exchange on time 2 would hit both of them.
Oh, okay. Because you have 2 registers. Okay. Got it. Okay, so we'll clear out the timer. DCA lift temp. TCF rep 11A -2. 1, 2. Which does an exchange with T liftoff. But, lift temp is what I saw. Okay. Oh, man. This is the hardest way to recode.
It sounds like you're getting it.
Yeah, but I mean, this is just like clearly they did a great job of making this self-documenting, like you said, but it's still like it's inscrutable because these addresses could mean anything at any time.
Yeah.
Okay. So we zero the timers. So we'll zero the timers before we do DCA lift temp and then a TCF back up. And then we get into another section. So TCF rep 11A -2. That just sets T lift off in phase 3. Oh, I guess, and then okay, so even though there's a label and rep 11 and rep and re P11, good Lord. So even though there's a label here, we're still gonna cruise through here. So DCA rep 11 essay, which I know we put something in there. Oh, right. Oh, yeah, here are these constants. So this is rep 11 essay. Oh, this 2 octal number is the address, not the value. Okay.
The number that you have highlighted there is the value of that constant. So that's going to load 77764 into the accumulator, into A, and 00013 into L. If you do a DCA on that.
Okay, and so I'm guessing that we're not going to execute this code because this is just for the compiler, right?
Right. Yeah, that's just a constant in memory that they're using to load into the phase registers.
Okay, so we had another label. So just since we skipped down here, we've gone through 3 different labels: rep11 and rep11, which basically just loads a constant and jumps us up. And then here's another label. Yeah, like this, like I can see how this is working, but like I don't understand what's being accomplished by doing this. It's so low level, grabbing individual numbers one by one and pushing them around.
So that actually gives like a nice little segue. We've just been talking about BASIC, but there was a second language that they used for programming this thing. So if you go to line 236, we can start talking about that.
My 236 or your 236?
We're looking at the same thing now, I think. I hope.
Okay. 236 for me is blank.
Interpret.
No. Which imprint was it? TC imprint?
Yeah, it should be around 236 at least.
Yeah, I'm way off. Let's go. Oh, 236. I must have gone to 263. Okay, 236.
All right. So yeah, there you go. So in addition to this BASIC language, which is just BASIC is just how the machine operates inside. They also had a surprisingly capable virtual machine they called the interpreter. And the interpreter was comparatively extremely powerful, but extremely slow. So you get into interpretive code by doing a transfer control to intpret, which is the entry point for the interpreter. And then after that, all of this code that follows is interpretive code. Just to give an idea of the difference between this and BASIC. The opcodes that follow are vload, OGC, which does a vector load. It's loading 3 double precision numbers as a vector. VSR1 shifts each element of that vector right. So it's essentially dividing each element of the vector by 2, storing the resulting vector in OGC. Then it does a vload on theta n, mxv, which is matrix times a vector. So they're multiplying that vector by the XSM matrix. The interpreter capability sort of goes on from there. It lets you do all sorts of matrix math. It can do vector projections. It's insanely powerful. You can accomplish a lot mathematically with a very small amount of code. It's just very, very slow.
And so that was executed by the AGC.
Yeah, so Impret as a routine looks at the return address. So you have to go to Impret with a TC. It looks at the return address and then starts loading data from there and then just interpreting it just like an emulator would, pretty much.
That's really cool.
It's super cool, and it's insanely powerful, and it's crazy that they managed to fit it into the memory that they had.
Yeah.
But it's the fact that you could encode all of this matrix math and everything into such a small amount of memory was like key to them being able to do the mission with, you know, just the 36 kilowords that they had.
Wow. Wow. Okay, that is genuinely the coolest thing that I've seen today. Like, you show me a lot of cool things, but like and the fact that you can just write the code to interpret in line is crazy.
Yeah, it's really cool. You may have picked this up as I was reading this off, but interpretive code is stored in a weird way. They wanted to have a lot more interpretive opcodes than they had basic opcodes. And they also wanted the interpreter. One of the nice features of the interpreter is that with one sort of asterisk, you can access anywhere in memory without worrying about what bank it's in. The interpreter will just internally switch you to the correct bank to load whatever number you want to access. And you can jump to any bank without having to manually fiddle with the banking registers. The asterisk is that for fixed memory, banks 0 through 17 can only reference each other, and banks 20 through 37 can only reference each other, and you're not allowed to have interpretive code in the super banks. But outside of that, like, you don't have to worry about erasable banks at all. It's all just seamlessly handled for you. And so in order to do that, they had to use the full 15 bits of a word for addresses.
Yeah.
Which leaves 0 bits for opcodes. So the opcodes have to be stored in a separate word. But it's really inefficient to just have a whole word dedicated to a single opcode. So what they did is they call this Polish notation. I'm not entirely sure why. But essentially, they store 2 opcodes per word, and then the addresses for each of those follow. So the first line of interpretive code here, vload VSR1, those are the 2 opcodes. OGC is the address that vload operates on, and then VSR1 doesn't take an address. And then the store codes are kind of a special case in that the address goes on the same line as the store. But then the next line after that, vload MXV, vector load, matrix times vector. The vload operates on a theta n, the MXV operates on XSM. So it's interesting in that you can be really efficient by pairing up your opcodes using Polish notation like this. For our reconstruction purposes, it gets very annoying because there's multiple ways to express the same thing depending on which opcodes you pair with each other.
Oh,
and then there's
Lord, this hurts.
one other feature. Oh, sorry, go ahead.
No, this hurts. Like, I'm having to let my brain go at a low level understanding and just let the more detailed stuff zip past me just to try to hang on to any of this. Okay, because I'm my brain's going, okay, matrix times vector. Okay, so I'm trying to figure out exactly what's going on. I don't need to know that. Just I can absorb the idea here. Okay.
Yeah, and one other feature of the interpreter that you'll see is that it has a concept of a stack. So you are able to push results onto the stack as you please, and then if you use an opcode that takes an address but don't give it one, it'll automatically pull the last thing off of the stack, which is another like memory saving thing.
And does it dynamically address the elements of that stack?
Yeah.
Cool.
Yeah, the interpreter is super powerful.
Was there a limit to how big the stack could be, or was it just limited by how much memory you had free at the moment?
Each job had dedicated memory that the interpreter was able to use for its stack. Okay. So I think you could have like 60 words on a stack per job. That might be too much. I might be thinking an octal. But it's on that order of magnitude.
Okay, so what were they using stacks for? Because like that's super powerful if you use them properly.
It's pretty much entirely simplifying storing of intermediate calculations when you're doing more math. So they'll calculate something, push it onto the stack, do some other math, and then pull that number off the stack to bring it back into the calculation.
Cool.
There is a document that I'm thinking of. There's in our not really that well organized document library on the virtual AGC website. There's something called the symbolic listing information for block 2. And that has a really good like introduction to the interpreter, and has a list of like, here's an equation, here's the most efficient way to implement this equation using the stack, sort of things.
Cool.
I sent a link to that one in Discord. I should try to compress that one. This was one of the first things that I scanned myself. So I've gotten a lot better at scanning documents since then.
Yeah, there are a lot of surprising things you don't think about. Man,
this document
I should have read through this before.
Despite its not really glorified presentation on the links page, this is probably the best singular reference for programming the AGC that exists. That is original. It's super involved and very good.
Yeah, I think you're right. Like I don't know what else exists, but like this makes a lot of sense.
Yeah. Funnily enough, this wasn't even written by MIT. This was written by TRW as sort of like instructions for their code reviewers.
Cool.
Let's see. Your download speed is faster than mine. I've almost got it here.
Oh yeah, I had it. Like I just clicked on it, and you were complaining about needing to compress it. I'm like, wait, I don't know how big. Like I was actually trying to think of a way to get Chrome to tell me the file size without going into my temp folder. So it's like, it's been a while since I've had to wait for anything.
It's tens of megabytes, I think, and it doesn't need to be. Let me see if I can find the section that I'm thinking of.
Mm-hmm.
Be just after this, I think.
This is OCR. I can search for something if you want.
Yeah, I did OCR it. My problem is just that I'm not sure what to search for. Oh, here we go. PDF page 232.
Oh, nice. There you go. Okay, so these are listed by equation and not really what the purpose of the equation is, but
yeah, they're I don't know that any of them really have any particular meaning, in as much as it's just an interesting equation for an example case.
Oh, okay. I love the handwritten square root sign.
Yeah, because their typewriter couldn't do it.
Yeah. So deload DMPR. Piddle squirt, great.
Yeah,
So store the first term in the push down list. So
Yeah, put PDDL is a push down followed by a deload. So it pushes down the current number and then deloads VAR, I think is what that is. Yeah.
okay,
And then takes the square root of VAR.
So it's starting with the square root term, or it doesn't start with a square root term. So what's deload DMPR H2? Oh, I see. HB are two variables.
Yeah, so it's deloading H, multiplying DMP is a double precision multiply with a rounded result is what the R means. So it's doing a deload DMPR, multiplying H by HB, pushing that down, and then taking the square root of VAR. Shift right 1 is the same as multiplying by a half. And then the DAD is a double precision add. And as it says, because DAD doesn't get an address, it takes the square root off of the push down list.
Yeah. So it never multiplied by 0.5, did it?
That's what the SR1 does.
Shift
right 1.
Yeah. You're right. Okay, so that gets us everything inside of the parentheses in the register.
Yep.
And then BDDV must be a divide command.
Yeah, BDDV is a backwards divide, I think is probably what the B stands for.
Okay,
it's saying
so inverse multiply, or inverse divide, I guess.
Right, yeah, it's saying divide D by this instead of divide this by D.
Sure. And then store var. So D would have been a memory address.
Yes.
Okay. And then store variable, and it doesn't give an address to store it in, but that's left to the reader.
No, var is the address to store it in. Store is the one exception that has the address on the same line as the opcode.
Okay, gotcha. Cool, man. It's I mean, it's not like these are super crazy. Okay, so example 3 has got some trigonometric functions. And I'm assuming that these are going to be their own constants. Oh, arc sign. So why is it a sign instead of? Oh, because it. Okay, great. Didn't read the problem. Cool. Okay. Var equals z component of d. I have no idea what example 4 is even supposed to say. Component of?
Z component of. So you have a vector and you're taking the third component of it.
Oh, I see. So D is an address. It is unit. So this is a three like a 3 tuple or something.
Yeah. So that's D unit. This is confusingly written. Is that a? So what is the code actually doing here? Okay, yeah, D is a scalar. So they're taking the scalar D, multiplying it by the unit vector of HB0 minus C, and then giving it the sign of the variable E. So if E is positive, it gets the answer is positive. If E is negative, the answer is negative.
What is a unit vector?
A unit vector?
Yeah, I don't think I know what that is.
So unit is just if you have a vector, to make it a unit vector, you divide it by its length so that the length is 1.
Oh, okay, that makes sense. And so how were they, let's say unit, how is that being actually written?
There's a unit instruction at the top of the next page.
Yeah, there we go. Okay.
So the first part of this is constructing the vector HB0 minus C, and then they do VDEF, which defines what they've constructed so far as a vector, and then they start working with it as a vector.
That's really cool.
Yeah, it's great.
So it's almost like you actually have access to object-oriented programming in a way. If you can say this variable inherits from class vector.
Yeah.
That's intense. Like, that's so crazy. No wonder this was so slow.
Yeah. Yeah. I think multiply, just like a multiply, is like 100 times slower than doing it in basic. It is quite slow, but it's insanely powerful.
Okay. So I think I need something simpler. Let's talk about compiling code, looking at checksums, and then maybe we can talk about the progress on the problem that we were talking about earlier.
Okay. So we've already hit the compiling step earlier. Just running make in the Comanche 45 directory compiles that code and then automatically runs the bank sum checker.
And so it compiles it to HTML files?
No, it compiles it to a binary file that's executable in the emulator.
Okay.
The HTML files are just like a byproduct that it spits out as well.
Okay,
you should see a Comanche 45.bin, which is what you would put into the emulator.
Would that be in virtual AGC?
No, it's still in the Comanche 45 folder.
Oh, okay. I scrolled past the C's too quickly, I guess. Oh, okay. Okay, cool. And then .buggers lists all of the checksums.
Yeah.
So
that is a file that I made from a drawing we got from the National Archives listing out all of the bugger words.
Oh, good. And the modules are defined somewhere. I feel like I saw those defined somewhere. Am I wrong?
You saw those, I think, in tags for relative set locks and blank bank cards. We didn't talk about this that much, but physically, in the Apollo Guides computer, your program gets divided up into 6 different core rote memory modules, which are numbered B1 through B6. So there's 6 memory banks per memory module. And I don't really know the exact reason for them settling on 6 fixed memory modules. It may have been mechanically that's what made the most sense for just putting together a whole bunch of rope cores. But what it did allow them to do is, if they had to re-release a program, they could get away with only having to remanufacture like one of the 6 modules in most cases, instead of having to reweave all 6 of them.
So you're can I take a look at the Python code that's coming up? That's actually Comanche 45.buggers is the original checksums.
Yeah. So the Python script that is actually used in IL, if you go up a directory and then into tools,
that seems
there's a checkbuggers.py.
Oh, nice. Okay. And then where's the output for the calculated buggers for this? When I built this,
they're encoded into the binary itself. So
okay.
The bugger words were added for use by the computer self-test. So the idea of that is that in order to check that all of your memory is working, the self-test program goes through the bank, sums up all the numbers in it, and if the sum of all the numbers is equal to the bank number, then it determines that bank is correct. it knows when to stop because so in the AGC, it's illegal to access memory that hasn't been allocated by your program. That doesn't actually get woven into the core ropes. They don't like just weave in zeros by default. They just don't weave those locations at all. And so if the computer tries to access those locations, it'll get a parity alarm. The parity check will be incorrect because it'll get all zeros. And then the computer just takes a hardware restart and goes back to the restart point.
Right,
So
because it's a 15-bit word because there's one bit for parity, and you want
yes.
I guess that would be an odd number of ones then if 0 doesn't count. Okay.
Yep, you got it. So the hardware checks for that as it loads every word from memory, and if it ends up getting an even number of ones, then it shuts down the whole thing, restarts. So to stop the self-check program from doing that, they marked the end of each bank with 2 jump to self instructions in a row. So just an address that jumps to itself, which having 2 of those in a row really doesn't accomplish anything. So they figured they would never ever have that particular sequence in a real program. So 2 of those in a row mark the end of a bank. In almost all cases, except after Apollo 5, they started running out of memory in a more severe way. And so they modified that rule a little bit to say that if there are only 2 locations left in a bank, then you put a single jump to self followed by the bugger word. Or if you're using all but 1 location in the bank, then you just have the bugger word at the end and no jumps to self. So that's sort of what the assembler does. When you assemble a program, it generates as many jumps to self as it can, up to 2 at the end of the bank, and then puts in the bugger word following that. And then everything else in the bank is unallocated.
Okay. So when you run make, where is it? Did it? Because I saw in the issue. Oh, there it is. Yeah, bugger word mismatch in bank 16. Actual is 70260. And expected this number, which is a diff of 10,000. Okay.
Yeah. So that's saying
like
the Python script calculated the sum of the bank, and it is seeing that. Well, it's not even really calculating. It's using that rule to determine which word is the bugger word, and then saying, okay, this is the bugger word that the assembler produced. This is what the drawing from the National Archive says it should be. And then I found it very useful to also print out the difference for just.
Yeah. Okay, so we've got load rope, we've got get bugger, we've got check buggers, which takes a rope file and a bugger file to get your diffs, basically. Okay, so argparse. I guess I don't know what the argparse library is, but it sounds like something I want to go look at.
It's a convenient way for dealing with command line arguments.
Yeah, that's I have. What was I doing? I had some script where I really wanted to be able to pass in arguments, and I did it without using an input. Like I actually took arguments, but I don't know if I used the argparse library. Maybe I did. Check bugger words of a rope binary against a known set. Okay, so you compile it first, and then you're going to go through rope file and a bugger file. So rope file is the binary. Oh yeah, there it is, binary file. Okay. Args equals parser. Oh yeah, okay. Check buggers. So we're going to do check buggers, and we're going to pass in the rope file from the arguments and the bugger file. Okay. Load rope. rope equals. What's array.array? I don't think I've ever messed with arrays.
Array is a module in Python that lets you easily load binary data of a particular structure. So this is saying load that file as however many 16-bit unsigned numbers as are in it. So it generates a whole bunch of 16-bit integers for me from that file.
Okay.
And then it also has a nice function to fix endianness.
I've never heard of that word.
Endianness is a bane of computer engineering. It's one of those things, you know. Endianness is the order in which bytes are stored in memory. Where little endian you store, like if you're storing a 4-byte integer, with little endian you store the lower bytes at lower addresses, which to the human eye looks backwards.
Mm-hmm.
And big endian you store the lower order bytes at higher addresses. So to the human eye, it looks like you're just reading the number forwards.
And which does AGC use?
The AGC doesn't really. I mean, bytes are a construct that came out after the IBM 360, I think. They're a much later construct. The AGC only thinks in 15-bit words, and it doesn't care.
Right. Yeah.
So this is really just a factor of the file format that we defined for our emulator, which is 16-bit big endian words, I think is what Ron used for the output of the assembler.
Okay, so byte swap fixes that. Shift off the parity bits. So rope is our binary that we loaded from the file and then swapped over, and it's just shift. Okay, so we're just dropping those. Okay.
Yeah.
And then we return rope. So that was let's see, load rope. Okay. So this is no parity.
Right. Yeah. This is ignoring parity for this calculation because it doesn't really matter.
Okay. So we're going to go grab the bugger file argument, throw it into buggers. Errors equals 0. Okay. So for line and buggers, strip. Okay. So we're going to ignore blank lines. We're going to ignore comments. Well, is that, I forget what your, so that's just the, I guess it's not in this one, but like this no. So it's like your license sometimes has semicolons.
Yeah, a semicolon is a really common comment character for assembly languages.
Oh, okay. And right. It was the buggers. Yeah. That's where I saw it. Okay, cool. Okay.
Yeah.
Okay, so we're only gonna look at these lines that reference banks. Okay, all right. Bank string, bugger string. Okay, split it by the equals and the spaces. Bank. Oh boy. Equals bank string. Okay, so interpret it as an 8-bit
as an octal number.
Octal number. There you go. Expected bugger. Bank and then okay, got it.
Yeah. So those are both octal numbers.
Gotcha. Okay. And then actual bugger, it calls get bugger and hands it rope and bank. Rope is the file, and then bank is the one that we just set. Okay, get bugger. If bank equals 2.
Yeah.
That's
So this is
octal.
This is a backwards compatibility thing because of a misunderstanding of how the hardware worked. The backstory for this is that back in the day, Ron Berkey, who started Virtual AGC, had almost no documentation and had the listings for Apollo 9, I think was the first one, and Luminary 131, which was almost the Apollo 13 code. And so he was essentially just basing all of his knowledge of the computer based off of what he was seeing in the listings. And due to particulars of how Hugh Blair Smith wrote the assembler, at the end of the listing, banks 2 and 3 are printed out before banks 0 and 1. Which is because banks 2 and 3 are fixed memory, they called it. They're always accessible no matter what bank you have. So that's where like the core operating system stuff lives. But because the listing was showing banks 2 and 3 before banks 0 and 1, the file format that Ron created for the virtual AGC emulator also puts banks 2 and 3 before banks 0 and 1, even though that's not really how the hardware worked. So this is just sort of accounting for that peculiarity of the virtual AGC file format.
Okay. So that gets us to there. Bank start, bank end. So, here we go. Now we're operating on rope. Okay. If TC selfs, which we're going to increment down here, is greater than or equal to 2, or I is equal to bank n minus 1. Okay, return rope I.
So all of this logic is just sort of encoding the rules that I was talking about earlier, where it generates up to 2 TC self instructions until it hits the end of the bank. So it's saying if you've hit the end of the bank, then the end of the bank is definitely the bugger word. Otherwise, if you have counted up 2 TC self instructions before this one, then this is the bugger word now.
Yeah, I see. I read too quickly and missed the S, man. You can't do these one character variables. Come on.
Sorry.
I got ADHD, man. I need at least like 4 characters before I even register it as something that I need to pay attention to. Okay, all right. So actual bugger. So we're just going to go into this. Oh no, that goes into the rope file. Gets the actual bugger and then matches. Okay. So this code is just checking them. It's not actually calculating them. Okay.
Correct.
Cool. All right. So that was way easier than I thought. Okay, cool. So I'm happy with that. So you use, man, I think my phone, my webcam software on my phone disconnects every time a notification gets displayed.
Oh, that's annoying.
Yeah, I am this close to asking for my money back. There's so many things in this software that just suck. Okay. Right. So to go back to the problem that we were talking about that started this whole thing, you're trying to track down a change to the code, and your initial guess of what that would have actually looked like based on the revision notes made checksums invalid. And so these are calculated just looking at the total number of ones and zeros, right? It's not looking at words in the I get what's the AGC file called? Is that assembler? The AGC
Yeah.
assembler code?
It is adding together the assembled value for each instruction. So in memory, there really isn't like a difference between a data constant and an assembled instruction. They just both look like 15-bit numbers.
Mm-hmm.
So the bank sum is calculated such that if you add together every location in that bank, including the bugger word, then the sum is equal to plus or minus the bank number.
Right. Okay, so I closed that one. I actually want to go back to it. Okay. So when you're pulling those out of the rope file, if equals S, okay, so basically this octal number is an address. Like how do you determine this is actually a TC, a TC to self?
There is a feature. This is sort of like a memory saving feature of the Apollo guidance computer. Any address stored in memory will act as a transfer control to that address if you jump to it. So an address constant and a transfer control to said address are the same thing in memory.
Okay. And so I think I followed you on the on why the addresses were actually kind of swapped around in the project code.
Mm-hmm.
But why are these numbers so round? Like why is that address a round number, I guess?
Do you mean the 2000 and 4000?
Yeah.
And 6000?
Yeah.
Um,
Is that just because of the length of a bank?
Yeah, that's the beginning of banks. So banks 2 and 3 are always available. And so no matter what fixed memory bank you have selected at the moment, bank 2 will always be accessible starting at address 4000. Bank 3 will always be accessible at address 6000. And then whatever fixed memory bank you have selected at the time goes into address 2000.
Oh, okay.
What this is saying up here is that, like, if you are in one of those two fixed memory banks, then the transfer control to self instruction is going to start with a 4 or a 6 because of their special location in memory, whereas all the other banks get swapped into address 2000, and so their transfer controls to selves will be 2000 based.
Okay, cool. I don't know why my brain decided that I needed to understand that, but okay. So how do each of these instructions get converted into those 15-digit words? I guess is it the instruction first or the instruction last?
Yule is it's a 2-pass assembler. So it runs over the code twice as it's generating code. The first time through, what it does is it looks at all the bank cards and sublocation cards and all of that, and says, okay, this instruction takes 1 word to encode, so my address is now 2001, and this next one takes 2 to encode, so my address is now 2003. So it associates a an address with each label, depending on just the size of everything so far. And then the second pass through looks at the value for each opcode and a value for each address, and puts those together to form the 15-bit word, using the labels that it established on the first pass through.
Okay. Okay. So when you're calculating your checksums to see if a change to the code that you've made is correct, are you ever just going, okay, well, I know that this instruction is 001 or whatever, and are you able to make those guesses in your head, or are you having to plug these things in and rebuild the code, reassemble the code?
For the most part, I'm just making guesses and then reassembling and seeing what happens. There are certain times where I've been able to make informed guesses based on the magnitude of the difference, and the banks pretty heavily cross-reference each other. So if I have a consistent error in a bunch of banks, sometimes I can look at the magnitude of the error in each bank and then say, okay, if I go to this other bank and add 2 instructions or delete 2 instructions, then it will make all of these other banks correct. So where in here can I get rid of or add these couple of instructions?
Could you explain that again? If they reference each other, isn't that just a TC or a TCF command in the bank that doesn't have a change? If it references another bank, how does that change the bank that's doing the referencing?
If you change the number of instructions in a different bank, and other banks refer to stuff later in the bank than that change, then the address that you're jumping to is different now. It gets shifted by 1 or 2.
Okay. All right, that makes sense. All right, I'm gonna pull up that issue. So okay, so all that to say, you're hunting for how this change was made, and when I was emailing with you, you were talking about Ron coming up with a totally different way to think about this, and I don't know, either I didn't read that far in the comment chain, or I didn't understand it when I got there.
It wasn't really a different way to think about it as much it was we were very convinced, like if you read how I wrote the issue, we were very, very convinced that this bug fix was the only thing they put into revision 45. And it turns out that we're now pretty sure that they snuck something else in too. And that something else completely resolved bank 17. So now we're down to just bank 16 that is wrong.
Oh, cool. So let's see. Okay, so bank 17 got down to a difference of 1 by adding vload, absolute val, store, delta v.
Oh, that one was just a coincidence. That sequence of that particular sequence of interpretive opcodes isn't actually valid.
Oh, cool. Okay. Okay, but it's indicating that basically it's cluing you into the fact that bank 17 has some combination of these things, or something that gets it close, and that puts you, the coding above is something like what it's supposed to be.
Unfortunately, that was really just exposing the weakness of having the checksums be straight sums of the words. It's a complete coincidence that got the difference down to 1.
Oh, it did. So how did he come up with this nonsense code? Do you know?
That code is close to what we want it to be able to do. The problem with it is that the way store is encoded in the interpreter, it looks exactly like an interpretive address. So what Ron was trying to do there was he was trying to use the stack. He was trying to get something off the stack with that vload. So he was trying to vload a vector off of the stack, take the absolute value of the vector, and then store it into del VSAB. But you're not allowed to have a store immediately following getting something off of the stack. There's a special, if you look down to my response, there's a special interpretive opcode called statter, STADR, and that forces it to get something off the stack and allows you to then have a store after that.
Okay. And that still only had a difference of 7, so yeah.
Yeah. Still unfortunately a coincidence as far as we know now.
Okay, so how did you figure out that it was a coincidence?
I'll send you a link. I think I linked it in the issue, but I'll send it in Discord. Ron was asking me how convinced I was that this was definitely the only change. And I was about to respond to him saying, there's no way they snuck anything else in. It was a point fix. But I like to get supporting evidence for statements like that before I make them. So
yeah, that's awesome.
We got from Debbie Douglas, who's the curator of the MIT Museum. Debbie is awesome. I sent her an email a few weeks ago asking if she could just take snapshots of memos in their collection related to this particular revision of software. That's not the link. Copy link. So she took just a bunch of pictures with her phone of various anomaly reports, and the first thing in that album is a memo that lists all of the things that are different between Apollo 9 and Apollo 10 in the command module software. And notably, it's revision 2 of this memo, and there are black bars written next to all of the things that are different from revision 1 of the memo. So I was going through here and looking at all of the things that are marked as different. COM4 is there in table B. That's the anomaly that we're trying to figure out the fix for, that we're still stuck on. And the list of PCRs, which are program change requests, there was one at the very bottom of that one, remove TVC DAP initial attitude errors. And that one was really frustrating for the Comanche 44 reconstruction, because we could see from this memo and from the GSOPs, the Guidance System Operation Plans, which were sort of MIT's publications about how the code worked, that this particular PCR went into Apollo 10. But when I tried to delete the initial attitude errors from TVC DAP, the bugger words went to hell. And so I had to have the initial attitude errors in there for everything to work out, which was really frustrating because we had this PCR stating that they were deleted. And so reframing, that was like a sticking point for me back when I was working on revision 44. But then coming back to this and looking at it again from the mindset of, okay, we have Comanche 44. If they were to remove the initial attitude errors for Comanche 45, how would they do it? And so I went back into that file and that particular code is very early in Bank 17, so you can't just delete it if you want to make a single module change. I mentioned earlier that one of the nice features of having the code split up into 6 different physical memory modules is that if you had a bug or something that you had to fix, you could get away usually with only changing one of those, which saved a significant amount of time and money. So presumably they would have wanted to make this fix in such a way that they didn't have to remake all the other modules, and most of the other modules refer to Bank 17. So they can't just delete this chunk of code from the beginning of Bank 17, because then they'd have to remanufacture everything, because the addresses that all the other modules refer to would be wrong. And so I went into the section of code that calculates those errors, and just, if you want to get rid of a bunch of code, one way to do that is to not and just put a jump instruction to skip right over it. And so I found the first instruction in that chunk, replaced it with a jump to go to the next chunk of that function after the attitude errors are calculated, and the Bank 17 checksum became immediately correct on the first try, which we figured was a pretty good indicator that that's probably exactly what happened there.
Nice. Okay, so that's in P30, right? That got that jump put into it?
That is in the file tvc initialize.
Oh. Of course, why would it be where I thought it was? TVC... Was that TVC what?
TVC initialize.
Oh, initial. Okay. I heard alarm at the end of that, and I was like, I don't see any TVC something alarm. Okay. TVC DAP initialization startup call. And so, like, where can you point me to the code that wound up getting deleted or jumped?
Yeah, so you're looking in Comanche 45 still.
Right.
Search for @init, ATTINIT.
In Comanche 45?
In TVC initialize. @init is the label in question there.
TCF to needle in.
Yes. So in Comanche revision 44, that TCF to needle in is a clear and add 1. So they're storing 1 into TTMP1. So that I replaced that clear and add 1 with a jump to needle in, and that seemed to do the trick.
So that was skipping that block of code. Looks like from PCR 747. That was in 45.
Mm-hmm.
And you had 45. Were you trying to fix 44 or 45? I thought you were trying to fix 44, right?
So where we are, we started with Comanche 55, which flew on Apollo 11. Worked backwards to Comanche 44, which was the first release for Apollo 10. We're now trying to get to 45, which was the second release. And then from there, we know how to get to 45 revision 2, which is what actually flew. So this is trying to get to revision 45 from revision 44.
Okay. So this is new code. It wasn't like you just saw it in a later version and just pulled it back into 45. You actually did add this.
Right. And so the reasoning here, if you look at the same function in Apollo 11 in Comanche 55, you'll see the results of PCR 749, which was TVC DAP initialization for CSM alone. The reason that they did not want to have this initial attitude calculation, or the initial error calculation, for Apollo 10 was because they discovered that if the command module and lunar module were docked, this code could lead to very large excursions at engine ignition. And so apparently what they did is for Apollo 10, they just removed it entirely by jumping over it. Search for add init. Just go to that same function.
There we go. I was trying to remember what I had searched for to get here.
Yeah. So in Apollo 11, you'll see what they're doing is they're looking at the current state of the spacecraft to see if the command module is by itself or if it's docked to the lunar module. And if it is docked, then it just skips to needle in and doesn't do this initialization. So the final solution to their problem here was to do the attitude errors, the initial attitude errors, only if the CSM is firing by itself. So mostly in like the trans-earth injection burn. But otherwise, it skips loading of these errors. But they either didn't have the time or the space, or hadn't decided on this as the final solution yet. And so for Apollo 10, they just apparently completely skipped over this calculation and didn't have the initial errors for either case. But it was based off of the Apollo 11 code there that I said, okay, well, if they're not going to be doing the initial attitude error calculation, then they're going to be putting a jump at the beginning of add init, and they're going to be jumping to needle in.
Cool. So you had to do that in combination with adding those three other instructions to fix the delta V magnitude error, right?
These are unrelated things, and apparently unrelated in the bank sums. So this is just another discovery that we made that happened to fix bank 17. So now we believe that the delta V magnitude error is entirely contained in bank 16.
Okay. Because right. Oh, right. Cool. That's so funny. You go chasing down one issue and you find another one.
Yeah.
It's very relatable. I feel like I've done that about 1 million times. Cool. Okay, so where are you now? I'm looking at Ron's comment from yesterday that lists high plausibility alternatives and reasonably. So is this, and not terribly plausible and implausible. So like we really have that many potential options that Ron, who's very knowledgeable and knows, like he already is starting with this huge list that he's built up.
I like how he put my example fix and not terribly plausible, even though it was the best thing I could come up with.
Well, I mean, to be fair, 2200, it ain't looking good, bud.
Yeah. So the problem is that as we were talking about earlier with interpretive code, because they're paired up with each other, there's really like hundreds of ways to insert this sequence of 3 instructions, and we just have to find the right one. And I don't know if there's a way to do it other than to just keep trying.
Yikes.
I can, if you want to see sort of why we're having this issue.
Yeah, that'd be great.
If you open up P40-P47 in both Apollo 10 and Apollo 11.
Okay, that was 40 to 47. Next, let's close some tabs. I don't need all these. And then P40 to 47. Okay. So this is 45 over here and 55 on the right.
Yes. So you're looking for the label S40.1. And the easiest way to get there, I think, is to search for S40.1b, because S40.1 is referenced everywhere. S40.1b should get you there pretty quickly.
Or I could do. This probably
Okay,
won't
yeah,
actually
so-
be faster, but I can do.
Yep.
No.
You're in the right place in Comanche 55.
Yeah, I got 55. What's. I forget the blank. Not blank. Yeah, there we go. S40. No. Nope, that's not white. Is that white space? Uh-oh. 55. Oh.
Yep.
See, this is what happens. You try to mess with regex, and you break everything.
If you're doing regular expressions, you could do just the caret S40.1 to match the beginning of the line.
Oh, yeah, you're right. I was going to do not a white space character, but I ended up typing shift or control W to close the tab instead of control shift W. All right, instead of, yeah, okay. So there we go. All right.
I don't know if this ever happens to you, but one of my pet peeves is websites that have a ton of hotkeys enabled by default, because I'll accidentally have like that window highlighted instead of what I'm trying to type into, and then I'll try to type something, and then I'll just fire off all of these hotkeys and not know what I just messed up.
Yeah. Although, like, as horrible as that is, my my main work software is browser-based, and they've disabled right-click.
Ah, that's
So,
horrible.
At this point, I would be okay with hotkeys. I actually ask them for hotkeys, and they won't. They'll go. Okay, so S40.1.
Yes. So if you look over on the Apollo 11 side, you can see the fix in place. They actually have it denoted as permitting a module only change. So the problem was that S40.1 assumes that the magnitude of your delta V vector is stored in the location del V SAB.
Mm-hmm.
And P30 was not correctly calculating that magnitude. So they had to insert these three instructions to load that vector, take the magnitude of it with appval, and then store it into the right spot. So if you copy those three instructions, vload appval, del VSN, store del VSAB, from Apollo 11 into the same spot in Apollo 10, and save it, and then go back into your command line and do make, you'll see very quickly why the change is not as simple as it appears on the surface.
Yeah, so it's just inserting these three, and then with the commenting on the following card.
Yep.
Oh yeah, I remember you copied this into the issue, right?
Right. So because a whole bunch of banks reference bank 16, just inserting those three words completely screws up everything else.
Oh, and I see. And so this actually includes that fix for bank 17 already, because I just grabbed it today. Okay.
Right. Yeah, I committed and pushed the PCR 747 thing last night under the assumption that that's correct, which hopefully it is. So the issue is that we have these three instructions that we have to insert somewhere in S40.1, but we have to do so in such a way that the size of S40.1 doesn't change.
Right. And by
which
size,
means,
you mean the number of ones doesn't change.
No, the number of instructions total. So the reason why a lot of those
'cause
bank
that
sum
would
differences
change.
that you saw were 3 were because those different banks had like a single reference to bank 16, and by inserting 3 instructions, you shifted an address by
Yeah.
3, and
Yeah,
so
yeah, yeah.
the difference became 3 wrong.
Yeah. Okay. Or 6 wrong if you reference it twice.
Yes.
Or 7 wrong. No. 3, 6, 9, 12, 15. So there's something weird going on with bank 24.
Bank 24 references it
Probably 4 times.
4 times.
And then
Yeah,
there's...
because 14 octal is 12 decimal.
Oh, duh. Okay. Okay. Wow. But at least you know that it's somewhere. How many lines is it? Oh, it's a lot of lines. So
yeah.
I mean, still, it could be a lot worse.
S40.1, S40.1b, and the constant theta con are the chunk of code that we're dealing with. S40.1 has to be in its place. Like that is definitely the address of S40.1 because it's referenced by bank 24. And then after ThetaCon, the next thing in bank 16 is S40.8, and that is also referenced by bank 24. So it's that chunk of code from S40.1 down to ThetaCon. So the way that they normally did this sort of change is that they would insert a jump to the end of the bank and then move some code to the end of the bank and then insert a jump back to where they came from. So in theory, anything in here could have moved to the end of the bank, potentially screwing up which opcodes are paired with each other. And then they have a jump back.
Right. And it could be anything in here. It's not just that these 3 instructions got moved. It's anything in here.
That is all we can definitively say. I would say it's probably more likely that those 3 instructions or something immediately around them what got moved. ThetaCon also sticks out because it's a double precision constant down there. So you need to insert 3 words into the bank, and that one is 2 words that you get for free just by moving ThetaCon.
Mm-hmm. And you can move ThetaCon to the end with no penalty.
Yes. But that leaves you 1 word short, so you have to move something else too.
And you got to do it. Well, so you have to move one instruction to the end, replace it with, what's the instruction for jumping, TC or TCF?
That's for basic. For interpretive, a jump would be go to if it's just a straight jump. If you want to store a return address, you can use call. Call lets you go back to where you came from with the interpretive opcode RVQ. And then there's also store instructions can be modified to do 2 things at once. So there's store just by itself just stores the number, but there's also stodl, STODL, which does a store and then a deload. Stovel, which does a store and then a vector load, or stcall, which lets you store and then call a function. So it's also possible that they got to the end of the bank by changing one of the stores or stodls or stovels to an stcall.
So do you have a rough estimate of how many possible places that jump could have been done?
Nope. It's a whole bunch. What I can say is that we have
here,
some dubious evidence that the number of words that got added to the bank was 5, which restricts the problem space a lot. Because when you're trying to add 3 instructions, just having 2 to get to the end of the bank and back isn't really a lot to work with. But the report that we got that number from is correct about the number of words in Apollo 10 and Apollo 11 and Apollo 9 for the command module. but it is wrong about Apollo 10 and Apollo 11 for the lunar module. And we can say that very definitively for some of the things that it's wrong about because we actually have those listings. So for this one, it's how much do we trust it? It's right about the two programs on either side of Apollo 10. So maybe it's right about Apollo 10. Maybe.
Whew, man, like it's funny when when we were talking on Discord and you're like, oh yeah, anybody can do this. You can, like, I'll get you set up and you can get cranking away. Like, you are assuming a huge amount of knowledge just to be able to, and I'm using the word "you," which really makes us an aggressive statement. But like, the assumption here is that you have all of this knowledge, which you certainly have. But like, I'm just thinking about what I would do to even just try out a couple of options. Not that I was, going to get lucky, just to roll, buy my lottery ticket. And like, I'm not even confident I could write a valid, like, even knowing how, like, what the strategy would be for, for moving something out. Like, I don't even know if I could write valid commands to even try one of these, much less go over all the possibilities that you have. Man.
The reason why I was saying that, like, background isn't really required is that interpretive code with its Polish notation, and it's so very different from any other programming language that I've ever encountered, that having background in other things doesn't really help you wrap your head around interpretive.
Sure. That's a good observation. Man, I this only makes me appreciate even more the work that you guys are doing. This is so freaking cool. And like, I love the fact that you're not making money off of this. This is just for the joy of figuring out what they did back in the 60s.
I would love if somebody would pay me to do this. Don't get me wrong.
Right.
But
heck, I would join an AGC boot camp if that was an option. Man, this is so freaking cool. Like, this is such a cool puzzle. Like,
yeah,
it's a puzzle with a reason.
I've been thinking a lot about. Like, it feels contained enough that we could write a program to solve it.
Mm-hmm. Yeah, that's exactly what I'm thinking. Is like how I would approach that.
But it's not easy.
Yeah. So we've got this list of 5, 6, 7, 10, 9 variously plausible solutions from Ron. Let's see. We're close to the end of the ticket here. PCR 747 being the change that added in it. Strongest hint that Apollo didn't fly with a working. What is ATT in it?
Addinit is the section of the thrust vector control code that sets up the initial attitude errors. So when we see like a PCR title refer to those, that's probably the function that it's talking about.
Okay.
Indy 91, by the way, that's Niklas Boig, who is the main developer currently of NASSP for Orbiter.
Oh, cool. That's really neat.
Yeah, he has been completely instrumental in all of these reconstructions as well, because he's very good at digging through documentation and figuring out when changes were probably made.
Having run out of plausible ways to code delta v sab absolute of delta v sine, proceed to follow up on the suggestion of looking at all of the changes in bank 16 between Comanche 54 code as it is today in Comanche 51. So for a bunch of small changes, Alex, I have. Simply tried out some of these monkey-like, whether or not they're consistent with change history. Change history only results in checksums of about 100. Yeah, okay, so that's a no-go. Oh boy, and here we are at the end of the thread. No, check into erasables makes no sense. Right.
Yeah, so he was just trying out random things that we knew changed between 10 and 11 to see if maybe they snuck one of those into 10, but none of them really work out. So if there is, I think we can pretty safely say at this point that if there is another change that they made to Comanche 45, that it's not represented in Apollo 11 for some reason. Either they added and changed their minds and got rid of it, or I don't know. And we don't really have any direct evidence that that happened. So with what we have right now, I feel pretty comfortable stating that this one fix for the delta V magnitude is the only thing left.
Especially,
there's no way to know for sure until we figure it out. But
I mean, especially if you can take that 5-word change as gospel. Yeah, I mean, it's not a heck of a lot of not a lot of wiggle room.
Right. Well, I mean, the 5 words, that's only for additions, right? The PCR 747 change to get rid of the initial attitude errors in TBC initialize, that was a net change of 0 words because I replaced one instruction with a different one.
Yeah.
So it's possible that they did another, like, simple patch like that somewhere, and that's throwing off our bugger words.
Yikes. Okay. I think it's time for me to go do something else because my head is absolutely swimming. But this is fantastic. Thank you so much for taking the time to walk me through this.
Yeah, absolutely. This has been fun.
Yeah, this is incredible. Like it makes me want to like sit down and have a conversation with you anytime you figure something interesting out, because this is just about the coolest thing to do with an afternoon that I can think of.
Yeah, it's a lot of fun. I appreciate
it. And for real, like this kind of puzzle needs to get turned into a game. Like come up with a fake space program or a fake spaceship, and we can come up with this, some reason that we need to reconstruct their code, and have some sort of a checksum and maybe a word count or something, and say, okay, here's a section of code that we know that the issue's in, go fix it.
Right.
That would be a really fun game. Okay.
Yeah, it's actually a lot of the revisions of AGC code that we've reconstructed so far have been sort of similar to that. Like there was a horrible bug in the first release of the Apollo 13 lunar module code that they fixed, and if you know what you're looking for, that one is very, very easy to find and fix.
Can you shorten sweet it for me? Like,
Hmm?
Can you short and sweet it for me, or do I not have enough knowledge to get it right away?
Oh boy, let me. It's been like a year since I did that one.
Okay,
so let me find it really fast.
Don't worry about it. We'll be here forever. Okay.
Okay. I'm pretty sure they deleted. Here, I think I know what happened. It's something like this, at least. What happened is they had a relative jump. Like we were talking about earlier, you can have a jump that's just like +2 or +3.
Mm-hmm.
I believe what happened is they deleted an instruction or a constant, and forgot to change a relative jump. So instead of going to code, that relative jump went to data or something like that. It was a really, really dumb, nasty bug, but it was easy to fix because you're just changing essentially the +2 to a +1 or something.
Yeah. And so the relative jumps are there just to save memory, right? So that you're not inserting more labels than you need.
The labels don't take any memory. They're just different names for addresses. The relative jumps are to... I guess it does save space on your symbol table, so you're not just completely flooding it with, if you want to skip a single instruction, you don't necessarily need to name the instruction that you're going to.
But that's just a Yule issue, right?
Right.
The spaceship doesn't actually care about that.
No, the spaceship doesn't care. The programmers might care if the symbol table at the back becomes bloated and it becomes harder to find what you're looking for.
Okay. It's such an interesting situation to be where you can make that trade-off. So yeah, we'll tolerate the bugs that get induced by using relative jumps.
I think they weren't expecting that many bugs. I just linked in Discord my pull request for the Apollo 13 bug. I think this is the only case of a relative jump bug that we're aware of that actually made it to a released program, at least.
Mm.
But the nice thing about the Lunar module code is that we have all of these memos from Don Isles that he scanned for us that describe in detail all the changes that they put into every revision. So with this command module code, that sort of history, if it still exists, we haven't found it. There were equivalent Colossus memos that Margaret Hamilton published, but she doesn't have them anymore, and we don't know anybody that does. So we're sort of flying blind with the command module code making these changes. For the Lunar module, it's a lot easier to figure out what happened.
Man, GitHub is such a great tool for doing work like this.
Yeah, it's great.
It's so great to, version control. So there's a project at work that I don't think that they use any version control for.
Oh, that's not good.
No, I don't want to. I don't know for sure, so I'm not going to talk about it. But just like the contrast in my brain is between seeing something with, a hobby project, like a fan historical project, being so thorough and having everything documented, and like you're able to just go pull up the conversation right away, and it's linked to the code. Like it's great. I love nerds. I just love nerds. Okay, well, I'm gonna let you go, but thank you so much for taking this time. Like seriously, if you come up with something interesting that you want to talk about, we can totally do another stream. We'd love to have you on the show. If it's like this was too complicated for the show.
Sure. Yeah.
But like, you call and we will come run, and we'll give you time any week if you are interested.
Yeah, I'd be down. I don't know if you've done like multiple person interviews before, but I can also pull in Carl and Ken and Mark if you want to do one on the restoration.
Yeah, that'd be a lot of fun. We've definitely done multi-person interviews in the past, so. It's one of those things where I know that this is fascinating. I just don't know what questions to ask. Like, I can invite anybody on, but if I don't say, "Hey, I want to talk about this thing," it's tough. So I appreciate the help in generating some of those questions that should be asked.
Yeah, sure.
Okay. All right. Well, have a great, afternoon for you, evening for me.
Yeah, you too, and happy holidays.
Thank you. You too. Stay safe, stay inside. Don't go talk to people.
I'll try not to.
All right. See ya.